Right, it's about 5:30, so we're getting ready to get started. Go ahead and chat me your first and last name if you haven't done so already. Again, just want to remind you, attendance is not something that I'm going to drop you for or whatever. But if you do miss too many days for this class, because you guys are my night class as opposed to my purely online class, if you do miss too many days, just make sure you keep in touch with me and let me know, hey, I haven't been there in a few days, or even a couple days, or maybe even a week, but I haven't dropped and I don't want to drop. Just let me know that. Another announcement I wanted to make was I want to let you know that I have been paying attention to the emails. I did send an email out after I graded the test, letting everybody know that there was several people, I think three or four, maybe five people that missed the face-to-face test. Uh, I just haven't had, I've got a lot of things going on. I just haven't had time to deal with that yet, but I plan on sending an email and or announcement out tomorrow. So I'll be doing that. So keep an eye on your email. What I'm leaning towards is probably letting you guys take it either this Sunday or maybe this coming Monday, something like that. So if y'all have a specific day that you can't do it, if you can't do it Sunday or Monday, or even Saturday for that matter, please send me an email, let me know so I can try to avoid that. My the plan is basically you can take it on a single day. That way, there's less chance of one person taking it and then telling another person what's on it, and then that person taking it, that sort of thing. So we try to have it all on the same day. But that means you have to take it sometime between just after midnight on. If I decide to do it Sunday, you'd have to take it just after midnight Saturday, so that you'd have till midnight plus 1 second a.m. up until 11:59, 59 seconds on Sunday night to take it. So that's the plan. But if you specifically can't do it on Sunday and you can't do it on, or you can't do it on Monday or you can't do it on Saturday, please send me an email. Let me know that. I'll try to take that into account. It might be that I have to make up. I already got to make up another one because these are all students that are taking tests, and all the other students have seen theirs. So I've got to make up a new test for you. But that would make me making yet a third test if I have to do it on multiple days. So please let me know, and do keep an eye on your email as well as the course announcements in Canvas. The last time we met, we were finishing chapter 5. I didn't get a chance to do the problem regarding drag force, but I did do it last night, and I let you guys know via announcement slash email. So y'all are supposed to go to, I think it was a 45-minute mark on the video that I posted from last night, and you can see an example of the drag force acting on a particle. So you'll learn about terminal velocity, that kind of thing. So make sure you check that out. We are going on into chapter 6 now, and chapter 6 is gravitation and Newton synthesis. So I'm going to start off by sharing my screen, my iPad screen with you guys. Anybody have any questions before we get started? You can just blurt those questions out if you have them, or you can type them in the chat. I am now looking at the chat, so I should be able to see that, but I don't see anything except for where people are posting their first and last name, which is good because that's what you're supposed to do for attendance purposes. So still no questions? All right. Well, I'm going to start off telling you basically what Newton was able to figure out. So, we didn't really have any idea or understanding of why the planets were able to orbit the sun, or why the moon was able to orbit the Earth, or why the Galilean moons, which at that time were called the Medicean moons, were able to orbit around Jupiter. And that was a problem, but Newton set out to explain that. And what Newton's idea was, well, basically, he had been studying light, and he had learned specifically that light obeyed a 1 over r squared law, meaning that if you, for instance, had some way of measuring the brightness of light, let's say 1 meter from a light bulb, and you got some brightness like 100 of whatever units that would be, watts or watts per square meter or something like that. If you actually got a number of like 100 watts at 1 meter, if you then went to 2 meters, that brightness would not be would not be 50, which would be half of 100. It would more likely be 25 watts per square meter or watts. And that what meant that it was a 1 over r squared law, meaning if you double the distance away, 1 over r squared means thumbs up, thumbs down because it's 1 over. And then r squared means if you double it, you change the number by a factor of not 2, but 2 squared, which is 4. If you triple it, you change it by a factor of not 3, but 9. If you quadruple it, it'll be 16. If you quintuple, it'll be 25. If you sextuple, it'll be 36. If you seventuple, it'll be 49, so on and so forth. So just on a whim, he said, well, maybe gravity acts like light. And he guessed that it might be a 1 over r squared hypothesis regarding the relationship between the distance away and the strength of gravity. And for this reasoning, he basically considered what is the acceleration of gravity on the surface of the Earth, which in principle is 1 Earth radius away from the center of the Earth. Well, the acceleration of gravity is 9.8 meters per second every second at the surface of the Earth. And then he said, okay, well, what about at the moon? What is the acceleration of the moon? Because what he had done was, and he says in his Principia that basically he was sitting under an apple tree. His mother owned an apple orchard. He was sitting under an apple tree when he looked up and noticed something similar regarding the apples in the tree and the moon. Specifically, he knew that once the apple got sort of infused with enough water that it was so heavy that the stem could no longer hold it, that the apple would be pulled to the ground by some force that the earth is exerting on the apple. And he said maybe that force is the same force that causes the moon, which otherwise would go straight in whatever direction it's going at any instant and continue to go straight. And since Newton's second law, or excuse me, Newton's first law said that an object in motion tends to stay in that state of motion unless acted upon by a net external force, that would suggest that the moon wouldn't be able to make this orbit. Instead, if it came right here, it would keep going straight. So the only way it doesn't keep going straight is if it makes a turn towards the center of the Earth and then another turn towards the center of the Earth and so on and so forth. So he said maybe that's the same force that's pulling that apple. And that apple, he knew, would have an acceleration of 9.8 meters per second. And he was able to calculate, like we did in the last chapter, the acceleration of gravity, or excuse me, the acceleration the moon has as a result of gravity. And we did that calculation yesterday and the day before for your class. But that calculation gave us that the acceleration of the moon, which was given by v squared over r, was 0.002725 meters per second every second. So he reasoned that if the law of gravity really is a 1 over r squared law, since the surface of the Earth is 1 Earth radius from the center of the Earth, and since the moon is actually 60 Earth radii from the center of the Earth, he would expect the acceleration of the moon to be one not 60th of the acceleration at the surface of the Earth, but 1/60th squared. And 60 times 60 is 3,600. And sure enough, if you can do this yourself, you can take 9.8 and divide it by 60 squared, which is 3,600. And lo and behold, you'll get 0.00272 roughly. I got 2725 when you calculate it this way, and I got 2725 when I calculated, excuse me, for the moon using the period of the moon being 27.3 days, which is only 3 sig figs. But when I did 3 sig figs again, calculating the 9.8 divided by 3,600, I got 2.7 or 0.002722 instead of 2725. But in no case is the 2 on the end of that or the 5 on the end of the number I got a sig fig, so it's not necessarily even relevant. So at that instant, upon learning that the moon's acceleration was exactly what you'd expect, namely 1 over 3,600th times the acceleration at the surface of the Earth, it was at that point that Newton was the only person on planet Earth that knew exactly why the planets orbited the sun and why the moon orbits the Earth and so on and so forth. Again, he didn't necessarily have a good explanation for it because it was what we call action at a distance. It was as if the Earth could reach out and pull on the moon, even though there's no physical connection between the moon and the Earth. So he realized that was a problem, but he also realized that he could solve a lot of outstanding physics problems. And of course, it wasn't called physics back then; it was natural philosophy. But he knew that he could solve a lot of big questions, answer a lot of big questions by assuming this was the case and reserving the understanding of how action at a distance works for some later generation. And that was the actual inspiration that Einstein took when he was trying to come up with his general theory of relativity. Like everybody else, he realized action at a distance was a problem, and Einstein's idea was a little different in that he did not think of force as gravity as a force, but rather ultimately he was able to picture it as a warping or a bending, if you will, of four-dimensional space, and that the planets are actually going as straight as they can, but space is all jacked up because it's got dents in it from the sun's mass, as well as from Mercury's mass and Venus's mass and Earth's mass and the moon's mass and so on and so forth. So what he was able to then come up with was a law of gravity, and he reasoned that obviously the larger the mass of the Earth, he would expect that the gravitational force would be larger. And then from symmetry, he argued that it would also depend on the other mass as well. So basically, what he was saying was that the force of gravity, F, was proportional to the product of the masses, m1 times m2, and inversely proportional to the square of the distance between them. And because of that, he was able to, of course, devise experiments and things like that to try to figure out exactly what this equation would be. And ultimately, what we found out was the force was actually given by a constant that we now call capital G, the gravitational constant of the universe. We don't call it capital G. We use the capital G to represent it, but it's called the gravitational constant of the universe, and it's G times m1 times m2 over r squared, where r is the distance between the point particle of mass m1 and the point particle of mass m2. Now, that being said, he was also able to go a little farther because he had specifically invented the calculus specifically to address this issue. Specifically, he tried to make sense of the nature of this gravitational force, and what he was able to show was that a spherical shell of mass would actually act on any object just like an object that was a point particle of the same mass but at the center of that spherical shell. He was able to prove that that was the case. So then it just became a matter of you don't have to assume M1 and M2 are point masses. We just know that any kind of spherical shell or any kind of spherical distribution of mass is going to behave just like a point particle at its center of mass. So we can say the R is the distance between the center of mass of M1 and the center of mass of M2. And of course, the force is a vector quantity, so it's not enough to just say what the magnitude is. We have to give the direction as well. Remember, that's one of the key aspects of Newton's second law. You can't just say that the acceleration is directly proportional to the net force and inversely proportional to the mass. You have to say it also acts along a line parallel to the net external force. So with this case, we say the force of gravity is directly proportional to the product of the masses, inversely proportional to the square of the distance between them, and it acts along a line that connects the center of mass of M1 and M2. And it's always attractive. So that's another key thing. We've never found a repulsive gravitational force that would require like a graviton and an anti-graviton, and we haven't been successful in finding any of those particles. So with that being said, I got to tell you, what is G? Well, it turns out G, at least to 3 sig figs, is 6.67 times 10 to the negative 11th, and the units have to be, hopefully you can figure this out yourself just looking at this, remembering that M1 and M2 have to have masses or units of kilograms, recognizing that F has to have units of newtons, and recognizing that R has to have units of meters. You'll get newtons meters squared per kilogram squared is the units of this gravitational constant. So notice it's zero, followed by a decimal point, followed by 10 zeros, followed by 667. So it's a really, really, really teeny number. In next semester in the 242 course, you'll learn that the force of the electric force, called the Coulomb's law, is of the same form. In fact, that force is F is equal to K Q1 Q2 over r squared. But in that case, the K is equal to 9.0 times 10 to the ninth. And in that case, it's newtons meter squared. And instead of mass, we have the unit of charge, which is the coulomb. So it's coulomb squared. So notice just by that comparison, we can already see that the electric force is 10 to the ninth times 9, which you might as well call 10 to the 10th, divided by 10 to the negative 11th. So we're looking at basically almost 10 to the 20th times stronger is the electric force than the gravitational force. Okay. So that's our law of gravity. Notice it also includes the wording about the direction. The force is always going to be attractive. It's always going to act parallel to the line connecting the center of mass of M1 and M2. And it's given by F equals G M1 M2. Any questions on that? All right. Make sure this, okay, yeah, it's still recording. I had paused the video earlier and I wanted to make sure that I hadn't accidentally forgotten to unpause it. Nope, I had. Okay, so we're good there. So, oops, someone else came in. Now I'm going to go ahead and start into the individual examples within the book. As always, this chapter is called Gravitation and Newton's Synthesis. The sections or subsections in it are 6.1 Newton's Law of Universal Gravitation, 6.2 is the vector form of Newton's Law of Universal Gravitation, 6.3 is gravity near the Earth's surface, 6.4 is satellites and weightlessness, 6.5 is the planets, Kepler's laws, and Newton's synthesis. 6.6 is moon rises an hour later each day. 6.7 is the types of forces in nature. 6.8 is a gravitational field. And 6.9 is the principle of equivalence, curvature of space, and black holes. As always, it starts with a chapter opening question, which you should take a poke at. And as your book mentions, this is basically information that you can find in Newton's Principia. It's called the Philosophiae Naturalis Principia Mathematica, but for short, we call it the Principia, which Newton wrote in 1687, or actually published in 1687, and was, in fact, written in Latin. So, anybody have any questions on that? All right, we're going to go to example 6.1. And 6.1, just want you to get an idea of how non-significant the gravitational force is, even though it is, in many cases, people call it the master of the universe. One of the reasons why they call it Newton's law of universal gravitation is because it's true for any two masses or any two objects that have mass, they're going to experience a gravitational force of attraction between them. That's period, no matter what. Long as two objects have mass, then they're going to be attracted to each other. And the other thing is, if you look at this equation, there's no value of r that you can submit into that F equation to get F equals zero. In fact, the individual gravitational force of every body reaches all the way out infinitely far away, and only at infinity does the force go to zero. So, with that in mind, let's look at example 6.1. So example 6.1, estimate. Can you attract another person gravitationally? It says a 50 kilogram person and a 70 kilogram person are sitting on a bench close to each other. Estimate the magnitude of the gravitational force each exerts on the other. Each exerts on the other. So I'm going to say M1 is equal to 50 kilograms, and I'm going to say M2 is equal to 70 kilograms. And I'm going to estimate R to be about half a meter. So 0.50 meters. That's a little bit bigger than, 18 inches apart. And what we're really trying to go for here is roughly the center of mass of one human, uh, and how far it is from the center of mass of the other human. So if you imagine two humans sitting on a park bench next to each other, essentially touching, it wouldn't be unreasonable to expect their spines to be about 18 inches apart. So that's what we're shooting for here. I can calculate that force as F is equal to G M1 M2 over R squared, and this is where I would normally write solution and then give you that particular equation. So I just wanted to catch up and do that. So we're looking at 6.67 times 10 to the negative 11th. Again, Newton meter squared per kilogram squared times 50 kilograms times 70 kilograms. So you can see now that the kilograms and the kilograms is going to cancel out with the kilograms squared. And then also you can see that the 0.50 meters, which is also squared, can cancel out with the meters squared up top, and you see the result will in fact give us a unit of newtons. And I'm really only looking for one sig fig here because it's an estimate problem. I'm going to put in all the numbers just to calculate it, and then I'll just report it to one sig fig. So 6.67 times 10 to the negative 11 times 50 times 70, and then divided by 0.5 squared, and that gives me about 9.33, or 9 times 10 to the negative 7th newtons, which is on the order of 10 to the negative 6 newtons, because 9 is essentially another factor of 10. So we can see this is roughly 1/1 millionth of a newton, which is not a huge amount of force. Remember, 1 pound is 4.45 newtons roughly to 3 sig figs. That's what it rounds to. So you can imagine that 1 millionth of a newton is really, really small. It's 1/4 millionth of a pound, for instance. Anybody have any questions on that? All right. So one of the things you should learn is, obviously we can do this type of calculation where we just plug in all the numbers and do all the math. But we should also remember, conceptually speaking, the force goes like 1 over the distance squared. So if you double the distance away, you cut the force down by a factor of 4. If you triple the distance away, then you cut it by a factor of 9. If you decrease the distance by a factor of 2, then you increase the force by a factor of 4, so on and so forth. So in this example, example 6.2, I'm going to show you one way we can take that into consideration. So example 6.2, spacecraft at 2 times the Earth's radius. What is the force of gravity acting on a 2,000 kilogram spacecraft when it orbits 2 Earth radii from the Earth's center? That is, it stays a distance equal to the radius of the Earth above the Earth's surface. And the mass of the Earth is 5.98 times 10 to the 24th kilograms. Assume a circular orbit. So that's the information they're giving us. They're saying mass of this object. That's I'll just call that the lowercase m, because obviously the spacecraft's going to have a lot smaller mass than the mass of the Earth, and that mass is 2,000, which I'm going to assume is 4 sig figs. So I put a little decimal there to make sure we knew that. The radius of the Earth is normally given this symbol right here, and it's roughly 6,380 kilometers, or 6.380 times 10 to the 1, 2, 3, 4, 5, 6. 10 to the 6th meters. That's the radius of the Earth. I should also say that the mass of the Earth is 5.98. Is 5.98 times 10 to the 24th kilograms. Now, I can give you all that, and you can use all of that to do this calculation, but it would really be kind of insane to waste all that much work. So really what we're going to do is realize the following. Solution. What we know is F is equal to G M M over R squared, and we're going to say R is equal to 2 times the radius of the Earth, okay? But we can also say that F is inversely proportional to the square of the distance between them. And what this means is, if R goes up by a factor of two, then the force, because it's inversely related, that's thumbs up, thumbs down. And that means on one side of the equation, the thing is in the numerator. In that case, we're talking about the force. And on the other side of the equation, in this case, we're talking about the radius, is on the denominator. Then that means those two quantities are thumbs up, thumbs down. So anytime you have, y equals something over x, then y and x are inversely related. It's also true if y equals some number over x squared or some number over x to the 1.5 power or something like that. All of those are inversely related, and that means thumbs up, thumbs down. But in addition to being thumbs up, thumbs down, it's also a 1 over r squared law. The thumbs up, thumbs down requires that when the r goes up by a factor of 2, the force is going down. So that's the thumbs up, thumbs down part, is the fact that these two arrows are opposite. Now, the other part, the fact that it goes like 1 over r squared, means it's not going to be by a factor of 2, but by a factor of 2 squared, which is 4. So what this means is whatever the weight, which, remember, gravity is the force that causes our weight. Okay. So whatever the weight of this 2,000 kilogram spaceship is, or I think it said, yeah, spacecraft, whatever the weight of it is on the surface of the Earth, if we move it out to twice the radius of the Earth, then it's going to be one fourth as heavy. So that's really the gravitational force of attraction between the spacecraft and the Earth when it's 2 Earth radii away. So we don't have to put all those numbers in. I didn't need to know the mass of the Earth. I didn't need to know the radius of the Earth. All I have to do really is say, okay, well, the weight at the Earth radius is equal to 2,000 kilograms times 9.80 meters per second. And of course, we know what that's going to give us. 2,000 times 9.8 gives us 1,000, or excuse me, 19,600 newtons for the weight. And of course, we only really had 3 sig figs there, so I have to underscore that. But that's the weight at 1 Earth radius. And then, since we know as r goes up by a factor of 2, f goes down by a factor of 4, so that tells us the weight at 2 Earth radii would equal 1/4 the weight at 1 Earth radii or radius. So with that in mind, I'm going to say 1/4 times 1,000, or excuse me, 19,600 newtons. And when I divide that 19,600 by 4, I get 4,900 newtons is the weight. And again, we only had 3 sig figs. So this is the force of gravity at 2 Earth radii. Any questions on that? So notice that was a lot quicker way of doing it rather than having to put in the 6.67, put in the Earth's radius, put in the Earth's mass and all that. We didn't have to do all that. All we had to do was calculate the weight at the surface of the Earth and then divide that by 4. You should, just to convince yourself that this is correct, you should go ahead and try plugging it in the equation for gravity and see that you don't get the same result. Don't be surprised if it's off a little bit, like instead of it being 4,900, maybe it'll be 4,896 or something, or it might be 5,000 or 4,980 or something, but pretty close. Any questions on this before we move on to the next one? All right, now we're going to deal a little bit more with the vectorness of this force. That's obviously a thing that you got to deal with, as we saw in chapters 4 and 5. F equals ma is a relevant part, and that was a vector equation. F equals gmm over r squared is a vector equation. So in example 7.3 here, or excuse me, 6.3 here, it says force on the moon. It says find the net force on the moon due to the gravitational attraction both the Earth and the sun. sun. Due to the gravitational attraction of both the Earth and the sun, assuming they are at right angles to each other, as in figure 6.5. So not only do they give us all that, they also give us various numbers that'll come in handy. So I'm going to write out example 6.3. And what they told us is the mass of the moon, which I'll call M sub L, the mass of Luna, which is basically 7.35 times 10 to the 22 kilograms. The mass of the Earth, which again is a circle with a plus in it, that is 5.98 times 10 to the 24 kilograms, and the mass of the sun, which we write as a circle with a dot in the middle for obvious reasons, and that one's 1.99 times 10 to the 30th kilograms. Now, we also need the radius of the moon's orbit, which we actually did before. So that's the radius of LO, which is the Luna's orbit, and that is 6.38 times 10 to the, no, that's the radius of the Earth. 7.3, no, no, that's not it either. Uh, where is it? Where is it? Where is it? The mass, it's 60 times the Earth radius. I know that, so we could actually do that. I was just thinking that they gave it to us here, but I don't see it at all. Okay, that's okay. We're going to say it's 60 times the radius of the Earth, and that is 60 times, and the radius of the Earth is 6.38 times 10 to the sixth meters. I can go ahead and write that 60 times 6.38 times 10 to the 6 meters gives me 3.828. That's 3.828 times 10 to the 8th meters. And remember, that is pretty comparable to what I said in previous lectures where I pointed out that the distance between the sun, or excuse me, between the moon and the earth is slightly bigger than a light second because it takes light about 1.25 seconds to get from the moon to us. And, that's pretty much what's happening when we see the moon. The sun's light is bouncing off the moon and coming to us, and it takes that light about 1.25 seconds to get to us. So we've got that. We could also use, of course, the distance between the sun and the Earth, and that distance is one astronomical unit, which is about 1.49 times 10 to the 11th. So the radius of the Earth's orbit is 1.50 times 10 to the 11th. I think it's 11th. Yeah, 11 meters. Sometimes they cite it in kilometers, and then of course the number ends up being like 10 to the 8th instead of 10 to the 11th. But I was trying to make sure I did the right one. So the diagram that they're talking about, let's go ahead and start off by saying solution. And the solution is where we state the equations that we're going to use. And in this case, that's G M1 M2 over R squared. But the picture that we're looking at here is basically when we're looking at a quarter moon. So we could imagine, for instance, the moon is this itty bitty body, and then the Earth is, say, this body, and then the sun, which we're obviously not drawing to scale, and none of this is drawn to scale, in fact, is over here. So this is the distance, well, that's one of the distances, and this is another distance, but the key thing to point out here is this is a 90-degree angle. This is the moon. Oops, I left it on making my drawings neat, and therefore it doesn't recognize handwriting very well. So there's Luna. Here's Solus. And here is Geo. So there's our Earth. And what we're trying to do again is figure out exactly what specifically it said, find the net force on the moon. So F moon equals F Luna equals question mark. So what we see here is that since these forces are all attractive, remember gravity is only an attractive force, so that means the force on the moon due to the sun acts along the line that connects the center of mass of the sun to the center of mass of the moon. So it's along this little vertical line right here, and we're going to say that this vector points this way, and this is F on Luna due to the sun. And then, in addition to that, the force on Luna as a result of the Earth will act along the line from the center of mass of the Earth to the center of mass of Luna, and it's going to be like this, and this force is F on Luna due to the Earth, and those are vector quantities. So we've got to figure out what those are, and then we have to add them vectorially. So the cool thing is with this formula, you just calculate the magnitude. You don't have to worry about anything. But then what you do is you make them into vectors. That's a little bit trickier task, but I suspect you know how to do it. Like in this case, these are very simple because I could just say, let's call this the positive x direction, and let's call this the positive y direction, then the vector force F sub ls would be whatever I calculate using g m1 m2 over r squared, and then I just multiply it by j hat. And then if I wanted F sub le, I'd take whatever I get for the magnitude and I just multiply it by I hat. That's it, right? Then we just add them, and that's it. But sometimes the force won't necessarily be right along an x-axis or a y-axis. In those cases, you have to figure out what angle it makes and then reduce it into an x component and a y component. So let's go ahead and start off by realizing that the total force on the moon, or F Luna, is equal to the force on Luna due to Solus plus the force on Luna due to the Earth, like that. So that's the equation we're using, and that's just the fundamental idea that vector or that forces are vector quantities. So now I'm going to go ahead and calculate the magnitude of the force of the moon on the moon as a result of the sun. Notice the wording I'm using here and the actual subscripts. I said F sub ls. That's the force on Luna as a result of Solus. So that's the first subscript is what's feeling the force, and the second subscript is what's causing the force. I'm going to leave the units off this time because it takes too much space, and I've already showed you how those worked out. So this is going to be 6.67 times 10 to the negative 11th. And then, of course, I've got the mass of the moon, which is 7.35 times 10 to the 22. And then I've got the mass of the sun, which is 1.99 times 10 to the 30th. And then I have all of that divided by, now we know really, to be honest with you, this distance from here to here, that is the 1.50 times 10 to the 11th meters. But to be honest with you, since this distance from here to here is so much smaller, remember this distance is 3.83 roughly times 10 to the 8th. It's literally a factor of 1,000 smaller. So we might as well say that this distance is also approximately equal to 1.50 times 10 to the 11th meters. So that's what we're going to use here. We're going to say it's 1.50 times 10 to the 11th. And then, of course, we've got to square that. And now I can say 6.67 times 10 to the negative 11th times 7.35 times 10 to the 22 times 1.99 times 10 to the 30. And now I'm going to divide that by parentheses 1.5 times 10 to the 11th. Only that quantity is going to be squared. And when I do that, I get 4.336 times 10 to the 20th. And that is newtons. And obviously I carried one extra digit beyond sig figs. Now I also have the force on Luna due to the Earth, and that one's going to be 6.6 7 times 10 to the negative 11th. And that's going to be times the mass of the moon, which is 7.35 times 10 to the 22. But it's also going to be times 5.98 times 10 to the 24 for the mass of the Earth. And then that distance is going to be divided by 3.828 times 10 to the 8th. And that quantity is going to be squared. So I take 6.67 times 10 to the negative 11th times 7.35 times 10 to the 22 times 5.98 times 10 to the 24, and then I'm going to divide that by parentheses 3.282, or excuse me, 3.828. 3.828 times 10 to the 8th, and then that quantity is going to be squared, close parentheses, and that gives me roughly 2.001 times 10 to the 20th. So what we see is in reality the force on the moon due to the sun, at least in this configuration, is a little bit more than twice as big as the force on the moon due to the earth. But we have to go ahead and compute this because, of course, we know when two vectors are added tail to tail, this is not a very scale drawing, by the way, but the way we do it when they're tail to tail is we are supposed to complete the parallelogram. What I want to try to do is try to make LE about half the length of L of FLS. So I'm going to go ahead and erase a little bit of this to make it a little more reasonable. It looks like we've got one, two, three, about 3 3/4 squares is the length of FLS. So I want this to be about two, somewhere around there. Oops. So this force is going to be roughly this big, and therefore, completing the parallelogram, we see that the total force should be this way. Okay, and with that in mind, we can say it makes an angle phi with respect to the line between the moon and the Earth. Uh, I don't know which one your book did. I forgot to make a note of that. Oh, they actually chose the other angle. So we'll get nine. We'll get the complement of the angle that your book did, but that's okay. All right. So how do we do it? Well, you can tell that these two forces are at 90-degree angles to each other. Therefore, the Pythagorean theorem applies for us to calculate the magnitude. So the magnitude of F uh, L is equal to the square root of the magnitude of FLE squared plus the magnitude of FLS squared, like that. And that's going to give us the square root of 4.336 times 10 to the 20th newtons quantity squared plus 2.001 times 10 to the 20th newtons quantity squared square root, and that gives us 4.336 times 10 to the 20th squared plus 2.001 times 10 to the 20th squared gives me the square root of 2.280 times 10 to the 41st newtons squared. And then when I take the square root of that, raising it to the 0.5 power, that gives me 4.775 times 10 to the 20th newtons, and that is the magnitude of the force on the moon, which we're calling FMRFL. So I get about 4.78 times 10 to the 20th. And now, of course, I can find the angle phi by saying phi. Oops, I should probably stick to blue or green or something. I don't know why I'm doing blue anyways, but phi is equal to the inverse tangent of opposite over adjacent. The opposite is FLS and the adjacent is FLE. So it's going to be the tangent inverse of FLS, which we saw had a mantissa of 4.336, and FLE had a mantissa of 2.001. They both had times 10 to the 20th, but that's going to cancel out anyways. So why not just take this part? So I'm going to say shift tangent inverse parentheses 4.336 divided by 2.001 in parentheses, and this gives me roughly 65.23 degrees. And I don't know where that six got a crazy looking hairdo on it, but anyways, I fixed that now. So that's roughly the angle phi that I've drawn. And of course, your book is solving for the complement of that angle. So you'd take that minus 90 or 90 minus that, and that'd be about 24.7 or 24.8 degrees. And that's it. But we would call that 65.23 degrees. Uh, in the negative direction with respect to x. I actually know this. We've got a weird coordinate system where x is pointing to the right, but y is pointing down. So technically, that's a clockwise, or that's a correct direction for a positive angle. So we just call that 65.2 degrees. Anybody have any questions on that? All right. So remember, one of the things that Newton was able to say was that you can imagine the Earth or any body that's actually trying to exert a gravitational force. If you imagine that as a sum of individual shells that are spherical, then each individual shell applies a force to anything out of it, outside of it, just like as if it was an object of the exact same mass, but was a point particle at the center of that spherical shell. And not only that, anything inside of that spherical shell would feel no force whatsoever. So that's a key thing to keep in mind. That'll come in handy when we start to think about how to add up forces and calculate the total force due to the Earth's due to the total mass of the Earth, and so on and so forth. Which we may or may not be put in a position to have to solve any of those type problems unless you happen to change your career from just pure physics and going out into calculating orbits and stuff like that. So anyways, we're going to move on. Just to tell you, if you wanted to try to construct a vector form of Newton's law of gravity, it would look like this. So Newton's gravity in vector form. So remember, we said F is equal to G M1 M2 over R squared is the magnitude of it. So what I'm going to try to do is imagine a three-dimensional coordinate system, X, Y, Z, and I'm going to imagine a vector that points to each of the masses, and then I'm going to try to figure out from those vectors what would I actually use as a vector to represent the direction of the force. So this is my right-handed coordinate system. Remember, right-handed coordinate system means if you hold up your right hand such that your index finger points straight ahead, your middle finger points perpendicular to that, and then your thumb points perpendicular to both of them, then X is represented by your index finger, Y is represented by your middle finger, and Z is represented by your thumb. And you can see that my version has that. So now what I'm going to do is imagine that there's a mass right here, and that mass is M1, and the vector that points to the location of M1 is going to be called R1. Now, in addition to that, and this, by the way, could be all sorts of places, but just to make it have some place in this three-dimensional diagram, I would say this is X1, this is Y1, and then if you draw this line like that and then draw one exactly parallel to it, what you'd find out is this is Z1. Now you might have another mass over here. Let's say this one is right here, and this, ooh, I wanted to draw that a different color. Let's say this one is right here, and this is mass M2. Then this mass might be up really, really high, and that makes y2 over here, and that makes x2 right here. And again, we could represent this as z2. So what we know is that the force is one attractive, and the force acts along the line connecting the center of masses of the two particles. So now I want to go ahead and draw my vector R2, which is going to give us the location of mass M2. So this is R2 right here. And you might not see this immediately, but the only two operations that you can do with vector R1 and R2 to give you a vector parallel to this line right here, which connects M1 and M2, is the subtraction of R1 and R2. So you could do R1 minus R2, or you could do R1 or R2 minus R1. It doesn't really matter. So what I'm going to do is I'm going to go ahead and say Newton's law of gravity in a specific form. I would like to know specifically the force on object 1 as a result of object 2. This is the force on M1 due to M2. So the force on M1 is a force that's pulling it towards M2. So specifically, that force should point this direction. Notice that that is an arrow that leaves R1 and goes to R2, and therefore that's exactly the direction that M1 would be pulled. Now, in looking at that, I have to realize that that vector R, or that red vector there, is R2 minus R1, which we can maybe call, for instance, R21 just to keep up with the order of the subscripts, and that would work fine. Only now, if I use that, then the force, if I put the force of attraction in terms of R21, that would be kind of weird, because then we'd get basically the 1 2 being on the force, and we get the 2 1 being on the R. So that would be kind of a bummer. So what we'd probably prefer to do is take the negative of R1 minus R2. So what we'll do now is, to make this into a vector, we'll say F12 is specifically equal to negative G M1 M2 over, now the vector that gives us the actual direction, I want to have the same subscripts, so I'm going to use the vector R12. And if you write a vector without its arrow on top, everybody understands that that is actually the magnitude of the vector. So I'll write it squared like that. And again, we're using the R12 because we really wanted R21, but that has a different order in the subscript. So it's better to keep the same order and then put a negative in front of it. And here's the weird thing. If I were to just put vector R12 on it like this, then we would run into the problem in that the vector R12 has a magnitude of R12. Therefore, we just multiplied the force by R12, and that made it, instead of G M1 M2 over R12 squared as the magnitude, now the magnitude is G M1 M2 over R12, but not squared. So what we do instead is use the unit vector instead. So we would say that would be the unit vector. Now, the way you go about making a unit vector is you take the vector itself and divide it by its magnitude. So what we can do is change this to just a regular vector and then change the superscript, or the exponent of R12 to 3. So another way we could write this is negative G M1 M2 over R12 cubed R12, like that, where R12 is equal to R1 minus R2. So that is the vector form of Newton's law of gravity. And hopefully that is a nice little exercise that helps you think about vectors in 2 and 3 dimensions and think about how to subtract vectors. I will tell you that your book has almost exactly the opposite formula because it's using F12 as where F12 is the vector force on particle 1 of mass m1 exerted by particle 2 of mass m2, which is a distance r21 away. The unit vector r21 points from particle 2 towards particle 1, and by doing that, that actually makes it r1 minus r2 by my notation. So that's why they have an exactly opposite formula as what we do. They still have the negative, but they use F12 and R21 instead, but they're doing something different. So with my explanation and my negatives and the explanation that I gave you right here for the name F12, all that makes it clear that it's exactly the same formula as the book gives, but I think in a better way. Anybody have any questions on that one? And just remember, if you want the total force on a single object, then you got to take the force on that object due to one thing, plus the force on that object due to another thing, plus the force on that object due to another thing. And you keep doing that for all the things that are applying forces to that one thing. So that's what we've been doing here when I said FLE plus FLS was equal to FL. Now we're going to move on to the next section, and this is gravity near Earth's surface. And what we want to do is we want to realize that weight equals W, which equals M times G, and is the gravitational attraction that the Earth has for, oops, for M. So what we used as weight equals mg is actually equal to the F, which is G, big G, M1, M2 over R squared. So with that in mind, we can say mg is equal to Gm, mass of the Earth, over, and of course, at when we use g is equal to 9.8 meters per second, we're assuming that the elevation of the object is specifically sea level. So we're taking the distance between the center of the Earth and the person, or the mass lowercase m, we're taking that to be the radius of the Earth. So this is going to be r Earth squared, like that. So you can see right there that the m's don't matter, and from that we've now reached the conclusion that gravitational acceleration is in fact the universal gravitational constant times the mass of the Earth divided by the radius of the Earth squared. And just to check, you can put all that in. You can say I'm going to just do 3 sig figs, 6.67 times 10 to the negative 11th times the mass of the Earth, which is 5.98 times 10 to the 24th. And then I'm going to divide that by the radius of the Earth, which is 6.38. 6.38 times 10 to the 6th meters. And that quantity is going to be squared. And when I calculate that, I get 9.799 meters per second, which obviously that's one extra digit beyond sig figs. So as we said, G is 9.80 meters per second per second. So that's what actually G is. G is the gravitational constant or excuse me, it's the acceleration due to gravity near the Earth's surface, and it has a value of 9.80 at roughly sea level. Okay. Now you might worry, well, what about if we're working at the top of Mount Everest, or what about if we're working at the bottom of the Mariana Trench? Well, those things matter, but as you're going to see with the next example, it's not going to matter that much. So let's go into example 6.3. Excuse me, example 6.4. Example 6.4 says estimate gravity on Everest, and there's a picture of our author Giancoli with two Sherpas that took him up to the top of Mount Everest, or at least at this point, he made it up to base camp. So, anyways, it says estimate the effective value of G on the top of Mount Everest, which has an elevation of 8,850 meters. If you read Into Thin Air, you'd know that's about 29,035 feet above sea level. That is what the acceleration due to gravity of objects allowed to fall freely at this altitude. Ignore the mass of the mountain itself. So, with that in mind, what we're asked to do is just to calculate G at Mount Everest. So, G at H is equal to 8,850 meters, which, by the way, is, of course, 8.850 kilometers, and I'm only doing that to let you know so we can see where it lines up to the Earth's radius in kilometers. So the radius of the Earth in kilometers is, of course, 6.380 times 10 to the 6 meters, which is 6.380. In this case, it's 6.380 times 10 to the third kilometers, like that. And you can see that basically the 8 lines up, or the 0 lines up with the 8 kilometers in the height of Mount Everest. So now we can go ahead and calculate solution. The gravitational constant is G times the mass of the Earth divided by the radius, or the distance from the center of the Earth to the location. So in this case, it's going to be R is equal to the radius of the Earth plus the height of Mount Everest. So that's going to be 6.67 times 10 to the negative 11th. Again, leaving the units off because it's just a pain to write all that. This is going to be 6.38. Now, remember the 8, which will round to 9 because it's 8,850 kilometers. 8,850 kilometers, or excuse me, 8.850 kilometers, not 8,000. I had the decimal right to begin with. So I'm just going to call that 9 kilometers, and 6.380 times 10 to the third kilometers would be, this is 6.39 kilometers. Yes, 6.39 kilometers. So it'd be times 10 to the third meters. Oops, I put that in the spot for the mass. That was not smart. Let's get rid of that. The mass of the Earth, of course, is 5.98 times 10 to the 24th kilograms. And then I'm going to divide this by, as I said, 6,389 meters. And that's going to be squared. So that's going to give me a different value than the 9.8, but I think you'll be surprised at how close it is. So 6.67 times 10 to the negative 11th times 5.98 times 10 to the 24th divided by 6,389 squared in parentheses gives me 9.772. Well, no, they were 9.772, not times anything. 9.772 meters per second per second. So just as a idea, what's the percent difference? Remember, percent difference is the difference divided by the average of the two, which is different from what most people would calculate. But I'm going to take the positive value, so I'm going to say that's 9.80 minus 9.77. No need in using an extra digit when I don't have an extra digit for the 9.80. And then I'm going to divide that by the average of the two. Clearly, the average of 9.77 and 9.80 is, you see that there's a difference of 0.03. So I'm going to go 0.015 on top of that. So that'd be 9.7. And now I'm going to say 85 because that's the average of the two. And then I'm going to multiply it by 100 and then stick the percent symbol on the side. So 9.80 minus 9.77 divided by 9.785 and then times 100 gives me 0.3, 0.307 minus, might as well say 0.307%. So not off by much more than not even a whole percent. It's really a 3/10 of a percent roughly that's off. So you can see even at the height of Mount Everest, which is the highest point on planet Earth, we're only off by 0.3%. If you did the Marianas Trench, which by the way, doing this calculation for Mount Everest and then doing again for the deepest part of the Marianas Trench is an extra credit problem you can do as well. And you'll see that that's also on the order of a few tenths of a percent different. So we don't worry about changing the 9.80 to different values because of altitude, unless you really need some highly precise work. Anybody have any questions on that one? Okay. Well, there's another neat problem. This is example 6.5. I'm going to separate this out with a nice straight line. And now I'm going to say example 6.5, and it says effect of Earth's rotation on G. Assuming the Earth is a perfect sphere, determine how the Earth's rotation affects the value of G at the equator compared to its value at the poles. So uh, we really, excuse me, we really just have a picture here to go by. We don't really have any data. So let me draw a picture to make some sense of what we're talking about here. So we've got the Earth like this, and what we're imagining is this is the pole and this is the equator, somewhere like that. Oops, equator and pole. What we're going to do is imagine a person standing up top there, and then imagine another person standing here, and both of them, of course, have a mass of m. And now I'm going to draw a free body diagram for each of them. So this is the person at the pole. So the person at the pole has a mass m, and the force acting on it would be, let's say, the force due to the scale, which would be really the weight, if you will, or the normal force. So I'm going to draw a green arrow upward. What would be that would be either the force of the scale, so I'll just call that F sub S. And you can imagine instead of the person standing there, they're actually standing on top of a scale, and you're asking what force is the scale reading. And then additionally, we have the force of gravity acting downward, and that gravitational force, of course, is mg. And because the Earth is rotating about an axis right through the bum of the person on the pole, the person's just doing like this, rotating like that, and therefore there's no centripetal acceleration necessary. So we can say the summation of the forces summation forces in the y direction equals mass times acceleration in the y direction, but the acceleration in the y direction is really going to be zero because, again, the Earth isn't rotating this way, it rotates this way. So with that in mind, we just get F scale minus mg is equal to zero. So the weight at the pole is just mg. Now we do the same thing, but this time we're going to do it for the person on the equator. And I'm going to draw this as if it's the x-axis, and I'm going to draw this as if it's the y-axis. And now I'm going to put my mass right here. And this time we have the force on the scale pointing to the left, and that is F scale. And then we have the force of gravity pointing to the right, and that's going to be mg. But in this case, the Earth is actually rotating this way. It's rotating about its center of mass, or about its axis, and because of that, the frame has to be recognized as accelerating. And in fact, that acceleration is in the red direction, which is a negative direction. So we're going to draw this right here and say the acceleration a sub c is equal to v squared over r. Okay, so now I can take the summation of the forces in the y direction equals mass times acceleration in the y direction, and this time the y is not zero. So we're going to get basically the F scale minus mg is equal to negative mv squared over r, like that. So I've got to actually, one, figure out what the velocity of the surface of the Earth is at the equator right there, roughly saying that the radius of the Earth as we know it is that radius, and using that and the fact that the Earth rotates on axis once every roughly 24 hours, we're going to go ahead and calculate V. So V is equal to 2 pi r over t, and the r is the Earth's radius, so that's going to be 2 pi times 6.38 times 10 to the 6 meters, and then that's going to be divided by 24 hours times 1 hour is equal to 3,600 seconds, like that. And that gives us 24 times 3,600. And of course, that's going to be 86,400 uh, is what the denominator is. So now I'm going to take 2 times 3.14159 times 6.38 times 10 to the 6. And oops, I wrote division there instead of multiplication, so that would have been a problem. So I've got 2 times pi times 6.38 times 10 to the 6, and then I'm going to divide that by 24 times 3,600, close parentheses, and that gives me roughly 464 meters per second. So that's the velocity. So now what I can see is Fs in this case is going to be mg minus mv squared over r. So I get Fs is going to be equal to m, and we'll just leave it as M. That's the more important thing, but I'm going to try to figure out what the rest of it is. So now we're going to say G, which is 9.80 meters per second, minus V squared, which would be 464.0 meters per second squared over 6.38 times 10 to the 6 meters, like that. And that's going to give us 4,000, or excuse me, 464 squared, and then divide that by 6.38 times 10 to the 6 gives me uh, 0.03734 or 3374. So it's going to be 9.8, or actually it would be 9.8 minus this answer. And that gives us basically m times 9.766 meters per second, which you can tell in terms of weight is actually going to be smaller than normal. Instead of m times g, it's going to be, let's say, 9.776 divided by 9.8 gives me 0.9966. So it's approximately 0.997 mg. So that really is the weight, the apparent weight of the object on the equator, and the apparent weight at the pole is that, and the apparent weight at the equator is that one. Anybody have any questions with that? All right, so there is actually a significantly bigger effect, as you can see here, or at least a comparable effect as a result of the rotation of the Earth, making the apparent acceleration due to gravity smaller or about the same size as, for instance, we got when we did the acceleration due to gravity at the top of Mount Everest. The top of Mount Everest, we got 9.772, whereas on the equator, we got 9.76. So it's actually a little bit bigger of a deal to be on the equator. It has a bigger effect than being at the top of Mount Everest. Now, if you also imagine being on the equator and then being at a great height, like at a mountain that's on the equator, then you have even a larger effect, and you might start to get to on the order of 0.6% as opposed to 0.3% difference in gravitational acceleration. But that also tells us that if you're on the pole, near the North Pole or whatever, you're going to weigh a little bit more than when you go to the equator. That's going to actually just give you a apparent decrease in your mass or weight, actually, technically. Anybody have any questions on that? Your book does talk to you a little bit about realizing that, in fact, the Earth is not an inertial reference frame. We're supposed to use inertial reference frames when we're dealing with F equals ma, for instance. The Earth technically is not a inertial reference frame. It is actually rotating, and it is actually accelerating too because it orbits the sun. But both of those are pretty minor effects until you start to get really high precision. So unless you're dealing with really numbers or trying to do calculations where you have multiple decimal places rather than just one or two decimal places, then you don't have to worry about it being an inertial reference frame. But if you're trying to go for two or three or four decimal places with some calculations, you might have to take into account the fact that the Earth is not a inertial reference frame. The next section is on satellites and weightlessness, and the one thing I want to tell you is if you read Newton's Principia, and by the way, Newton did actually write another book. I forgot the title of it now. I have it in electronic format. I don't have it in a bound version, or I could just look up at the title. But he wrote a book for laymen, if you will, that would explain his understanding of physics. And in that, he had a good little picture. I think I saw the same picture, in fact, on the Principia as well. But what he pictured, far as planets and objects leaving the Earth and stuff like that, was actually. Let me go ahead and draw a good circle. So, his picture for his popular book was imagine the Earth with a mountain on top of it, and actually the program tried to make it a little better than it was. I'm sort of trying to draw that Devil's Tower from Australia or whatever. But anyways, if you imagine firing a cannon off of here, this would be a good explanation of how you go about setting something in orbit around a planet, or how you'd actually imagine shooting a projectile that could escape from Earth. So what you would do is you imagine shooting a cannonball from a great height, And if you shot it, it would fall and land right here. If you shot it a little faster, it would fall and land here. If you shot it a little faster still, it would land here. Faster still, it would land here. Faster still, maybe land here. And in fact, about the fastest you can go before anything really exciting happens would actually make it land just on the opposite side of the Earth. But if you gave it just a little bit more speed from there, then what would happen is the object would come out like this, and it would get closer and closer and closer and closer to the touching the Earth, but it would just barely miss the Earth. And then, because gravity's trying to pull it, it would actually start to get up a higher distance, a higher distance, a higher distance, and it would come back in. And if you could ignore the air resistance of the atmosphere, then it would basically run right smack into the back end of the cannon that fired it. Something like this. So you can see right there that this distance is longer than this distance. This distance is on the order of the radius of the Earth, where this distance is on the order of the radius of the Earth plus the really tall mountain, whose height is h, like that. So what we see is if you try to fire a cannon to escape gravity, what's going to happen is if you just barely get it to sort of escape in some sense, then it will go into an orbit, and that orbit will be elliptical. So this blue line is an elliptical. Now we don't know this yet. Uh, Historically, I'm just telling you what Newton said, and actually Newton knew it. Newton worked out, in fact, that with there's only two forces of nature that Newton was able to show that could actually have a closed orbit, and he said the force is a force that's proportional to distance, which is what we call Hooke's law, the force on a spring, F equals kx, and the other force is a 1 over r squared law. Those are the only two forces in nature that Newton was able to conjure up that actually allows for closed orbits. That means an orbit where an object can, take off and then will circle back and be back at that exact same spot with that exact same velocity. That's a closed orbit. And he said that only happens when you have a force like F equals kx or a force like F equals k over r squared. So he was able to do that. And then he went further and said, in fact, any of those, either of those forces will produce orbits that are what we call conic sections. So the possible orbits are conic sections. And what we just showed is the slowest possible orbit you could get, the least energy orbit you could get would be an elliptical orbit. If you decided to shoot it a little faster still, then it would basically miss the other side by a little bit more than it did before, and then it would come back in about the same height, and you could do that again and again and again until basically you would get to the point where it's actually the same distance around, and at that point it's a circular orbit. If you went faster still, then at that point it would do something like this, and now it's an ellipse again, only this time the ellipse is higher on the opposite side. In other words, the long axis is on the opposite side of the Earth. So this is another elliptical orbit. And this is the slowest. The second slowest. And this is the fastest of the closed orbits. If you go further still, then what's going to happen is it becomes a parabola or a hyperbola. So at higher speeds, the the projectile leaves the orbiting, the orbit of Earth and follows a parabolic or hyperbolic trajectory. So that's what really happens if you try firing a cannonball off of a mountain on the surface of the Earth. You can speed it up, speed it up, speed it up. Eventually, you'll get fast enough where it'll just miss the Earth's surface on the opposite side of the Earth, and it'll be in what we call an extremely low orbit. And in fact, it's likely that you might have to go a couple more times because it might actually land on the opposite side of the Earth, meaning it make a full 180 and then land a little bit past 180 degrees, or even further past, even maybe 270, just because we're losing so much energy to the atmosphere. But eventually, you could get going fast enough where it would miss the bottom of the Earth and then also miss the other parts. And because of that, it would establish an elliptical orbit. And if you sped it up more, it would be still elliptical, but closer to a circle, more, still elliptical, but closer to a circle, more, and then you get a perfectly circular orbit. And then more, you'd get elliptical orbit with the long part a little further down instead of up where the mountain was, and then more elliptical and more elliptical and more elliptical. And then, in fact, if you're able to just give it enough speed where it is able to get infinitely far away from the Earth and just come to a stop, then you're talking like a parabolic orbit. Or if you actually are able to get out to infinity and still have some kinetic energy left or some speed left, then it might make a hyperbolic orbit. So that's really what we learned from the orbits and the sense of how to make something orbit. And in addition to that, we learned that, in fact, when we talk about the astronauts being weightless, they are experiencing weightlessness. And as I mentioned before, it's because it's a microgravity situation. You can tell, for instance, the gravitational acceleration at the surface of the Earth is 9.8. And in fact, when you get up to the height of the moon, the gravitational acceleration is 0.00272 meters per second. And that's really a strong factor smaller than 9.8. So that's why astronauts refer to it as microgravity. But in reality, the reason why you're actually experiencing weightlessness when you're orbiting the Earth is because you're constantly in free fall. So just like when you go over a railroad track in your car a little bit faster than you meant to, you feel sort of butterflies in your stomach, or if you go on a negative G turn like in Apollo's chariot at Busch Gardens, when you do that, you feel a little lighter, and that's because you're actually experiencing weightlessness. So remember that it's not correct to say that astronauts in space are weightless because there's no gravity in outer space. That doesn't make any sense because we know for a fact that when astronauts are orbiting our Earth, they're orbiting closer to the Earth than the moon is, yet the moon is being held in orbit around the Earth by the Earth's gravity. So clearly, reaches out further away. So it's not that there's no gravity in outer space, it's that the astronauts being in orbit are actually in free fall. And that is what makes them experience weightlessness. Any questions on that? All right, so let's look at example 6.6 now. Example 6.6 says geostationary satellite. A geostationary satellite is one that stays above the same point on Earth, which is possible only if it's above a point on the equator. Why? Because the center of a satellite orbit is always at the center of the Earth. So it's not possible to have a satellite orbiting above a fixed point on Earth at any latitude other than 0 degrees. Geostationary satellites are commonly used for TV and radio transmission, for weather forecasting, and communication relays. Determine A, the height above the Earth's surface such a satellite must orbit, and B, such a satellite speed, and C, compare the speed of the satellite orbiting 200 kilometers above Earth's surface. So A, we want to know the height, A, height of oops, height of geostationary orbit is equal to question mark. B, we want to know the such a satellite speed. So speed of geostationary spacecraft. And C, they want us to compare that speed to the speed of a 200-kilometer height orbit. Compare to speed with, oops, h equals 200 kilometers. So that's what we're trying to do here. So what I have to do is first establish a Newton's second law so we can get some sense of exactly how fast things have to go and that sort of thing. So I'm going to use my program to make a really nice circular picture of the Earth. And what we're going to have is an object orbiting it. Let's say this spacecraft, right? Oops, I got to take it off that special drawing thing because it always messes up there. So let's say this is our spacecraft. Okay, so it's flying over. It's obviously a car without wheels, but anyways, this distance from here to here is the radius of the orbit. Okay, and when we draw a free body diagram for that, we're looking at it as a snapshot in time, if you will. I'm going to call this downward direction the positive y direction, and I'm going to call this leftward direction the positive x direction, and I'm going to say the object has a mass m is right here. The forces acting on it, of course, are the gravitational force, which points in the positive direction, and that force is the force due to gravity. And the other thing that we have to know is really that's the only force because in outer space, at least when you're really far from our atmosphere, there is essentially a vacuum. It's not exactly a vacuum, but it's pretty darn close. It's more of a vacuum than most of the places or most of the vacuums that we can create on Earth. We can get more like stuff we'd see in molecular clouds. We can get that level of vacuum on Earth. We can't get the other levels of vacuum. So that's G M M over R orbit squared is what that force is. But in addition to that, we have to realize that the acceleration has to be in that direction right there, and that's A is equal to V squared over R. Now, what we want is for geostationary orbit, we need the period T must be 24 hours. Now, there's a little bit of differing there. There's a sidereal day versus a solar day. A sidereal day is the time required for the Earth to make a 360-degree rotation. And it turns out that in order for the Earth to turn such that the moon, or let's say such that the Earth is directly over a specific latitude, the sun is at a specific latitude directly above it on the Earth, and you wait until that Earth is over that same latitude again, or excuse me, longitude again, then that is what we call a day. That day is 24 hours, but that actually requires a rotation of not 360 degrees, but about 360.986 degrees. So technically speaking, the 360 degree rotation is about about 24 hours, 56 minutes, something like that. But we're going to ignore that and just treat it like it's a 24-hour day. So with that in mind, I got to figure out what the velocity is. So the velocity of the geostationary orbit would be 2 pi times the radius of the orbit divided by the period of the orbit. And of course, we need to figure out what the height of that orbit is. So we need the r as well, but we also need the t0 to be what it is. So with that in mind, we can go ahead and set the summation of forces in the y direction equals mass times acceleration. So I'll say the summation forces in the y direction equals mass times acceleration in the y direction. And in this case, we're going to have g m, mass of the Earth, over the radius of the orbit squared is equal to mv squared over the radius of the orbit. We can see right now that the m's are going to cancel out. We can also see that one of the r zeros is going to cancel out. And from that, we can see that we can either solve for v or we can solve for r0, or we might be able to use the two to help us out with that. So I can now say that let's solve for r0. So I'm going to say R0, ooh, I should stick to the green. I'm going to say R0, which is now going to come to the right-hand side and be on top. And now I'm going to get R0 is equal to G times the mass of the Earth over V squared, like that. So now I've got R0 in terms of V, and I can, and of course that V is still the V of the orbit, so I can subscript that O as well. So now I can substitute this R0 from equation 1 into this equation 2. So plugging 1 into 2 will yield the following. V0 is equal to 2 pi. And now in place of R0, I'm going to say Gm over V0 squared divided by T0, which T0 is a quantity we know. But from this, you can actually see that I get V0 squared, or excuse me, V0 cubed is equal to 2 pi g m the Earth over t0, like that, and that allows us to at least solve for the velocity. So now I can solve for the velocity, which is part B. I would have preferred to get part A first, but sometimes you just don't, so that's okay. So V0 is actually going to be equal to the cube root of 2 times pi times g times the mass of the Earth over t0, like this. So that's going to be the cube root of 2 times pi times 6.67 times 10 to the negative 11th. That's Newton meters squared per kilogram squared. I hadn't worked out these units for you yet, so I wanted to make sure I put the units in it. The mass of the Earth is 5.98 times 10 to the 24th kilograms. And then the period is supposed to be 24 hours, which is 86,400 seconds, like that. And from this, we can see that one of the kilograms is going to cancel out. And we're going to have, for instance, units of, I'll work these units over here in the red just to keep track of it. So I've got a Newton meter squared per kilogram squared times a kilogram, and then divided by a second. And you can see that this kilogram is going to cancel out with that kilogram, and the Newton is a kilogram meter per second squared. And I also had a meter squared up there, but I also have divided by kilograms now. And if I took that second, I can actually multiply that by the denominator, so it's a kilogram times second down here. Now what we see is I've got kilograms canceling out with the kilograms. So this kilogram cancels out with that kilogram. But now I have, in fact, meters cubed over seconds cubed. and we're taking the cube root of that, so that's exactly what we want. That would be the meters per second. So we now see that the units work out great. I'm going to compute the number now. This is going to be the cube root of this quantity. And what's that quantity? 2 times 3.14159 times 5.98 times 10 to the 24th. And then I'm going to divide that by 86,400. And that gives me 4.349 times 10 to the 20th meters cubed per second cubed, like that. Now I take the cube root of that, which is the same thing as raising it to the 0.333333 power, and that gives me that the velocity is 7.576. This looks way too big. Yeah, that's way too big. Times 10 to the 6. I got to check my units. I got to check my calculation real quick and see if I did everything correctly. I said 2 times 3.14159 times 5.98 times 10 to the 4th. Oh, there you go. I did not include G in that calculation whatsoever. So there's the problem. So let's erase that figure under the square root because that's clearly a mistake. Evidently, in my calculation, I did everything but G, so that's why it came up with such a weird value. So let me try again. 2 times 3.14159 times G, which is 6.67 times 10 to the negative 11th, times 5.98 times 10 to the 24, and then I'm dividing that all by 86,400, and that gives me 2.901. Whoa. That gives me 2.901 times 10 to the 10th meters cubed per second cubed, like that. And that means the velocity for this orbit is the cube root of that. So I'm going to raise it to the 0.333333 power. And that gives me roughly 3.073 times 10 to the third meters per second. So that's literally 3,000 meters per second, which is about 7,000 miles per hour. So you can tell that's pretty darn fast. I think it's 7,000 miles per hour. Uh, Double check that real quick. I think your book actually calculated. So yeah, it's about 7,000 miles per hour. So we have that figure for the initial velocity. That's actually the answer to part B. So I'll put a B on it like that and I'll box it off. Now that I have V0, I can also get specifically R0. We know, for instance, that V0 is equal to 2 pi R0 over T0. So that means R0 is supposed to equal V0 T0 over 2 pi. So if I take 3.073 times 10 to the third meters per second and multiply that by 86,400 seconds and then divide that by 2 times pi, that should give us what our radius is. So I'm going to take this 3.073 times 10 to the third. I'm going to multiply that by 86,400, and then I'm going to divide that by parentheses 2 times 3.14159, close parentheses, and that gives me roughly 4.225 times 10 to the 7th. And in this case, you see the meters per second multiplied by the second. So this is just meters. So we actually have that the distance for the orbit, which is from the center of the Earth to the orbit, is 42. Well, if we tried to do this, it'd be 4.225 times 10 to the fourth kilometers. So this is like 4,000. No, 42,225 kilometers, or actually 42,250, 42,250 kilometers like that. Now, in order to figure out the height, which is that's what we're wanting to know. The height is 42,250 kilometers, which, by the way, that only had three sig figs, so the 50, the 5 and the 0 were not sig figs. And now I'm going to subtract from that the actual radius of the Earth, which is 6,380 kilometers. So if I divide this by 1,000, that would give me the number of kilometers. And now I subtract from that 6,380, and that gives me essentially H is equal to 35,870 kilometers is H. So there's our part A. So we're looking at 35,000 kilometers above the Earth's surface. That does agree, by the way, with the same result the book got. And if you want to actually calculate what the velocity of the orbit is for 200 kilometers, what we can notice here is that the velocity of the orbit turned out to be basically, I will borrow this expression for the velocity of the orbit. Let me highlight it like this and then copy it to the other page. So I'm going to say copy, paste, like that. So that's the velocity of the orbit that we had. If I had a orbit that was different though, no, I can't use that formula either because that formula doesn't have the actual distance. So what I'm going to do is set back to what we had from Newton's law of motion with Newton's law of gravity. What we had was mv squared over r is equal to gm m earth over r squared. And with that in mind, we can go ahead and cancel out the m's, and we get v is equal to the square root of g times the mass of the Earth divided by, oh, actually, yeah, divided by just plain r, because when I pull the r to the other side, it's going to cancel out with the r squared in the bottom, and that's it. So I can do this, but what we had was the v of the orbit was the square root of g m over the radius of this orbit, and the v at 200 kilometers was equal to the square root of gm, but instead at 200 kilometers above the Earth's surface, which would be 6,580 kilometers. So that would be 6,580 kilometers. So what we can see is that if I took v 200 kilometers and divide it by v orbit, what would happen is I would get gm over r0 divided by g m over r200. And you can see that basically the g here and the g here and the m here and the m here would cancel out, and that would give us that specifically the velocity at 200 kilometers would equal the square root of r200 over r0. So we already know what the, oh, excuse me, I left off a part. All of that times the velocity of the orbit that we had before. So the velocity at 200 kilometers would equal the square root of, as I said, 6,580 kilometers over the velocity that we had before, or excuse me, the distance that we had before, which was 42,250. So I'm going to put that over 42250 kilometers. Notice that's in kilometers as well. And then all of that times the velocity that we had, which was 3,073 meters per second. So if I take the 3,073 and multiply it by the square root, and gotta find my square root button, square root of 6580 divided by 42250, that gives me 1,213 meters per second. So the velocity is markedly larger. And in fact, this is more like on the order of uh, 17,000 miles per hour, or excuse me, 17 miles per hour versus 7,000 miles per hour. Anybody have any questions on that? All right. So we've talked about weightlessness. We've talked about calculating orbits, so on and so forth. What we need to do is now talk about Kepler's laws. So, what actually happened around the time of the Copernican revolution and also around the time of the scientific revolution, which I treat those as two separate things. And the reason is Copernicus was basically going by the teachings of Aristotle and said, you know, we've lost our way from what Aristotle taught us. We've got a crazy model. They had the Ptolemaic model of the universe, which in these times the universe was literally just the sun, the Earth, the Moon, Mercury, Venus, Mars, Jupiter and Saturn, and then maybe 7,000 stars, 10,000 stars, something like that. That was the entire universe to them. They didn't understand that our solar system was in an island of stars called a galaxy, and they didn't realize that there were other galaxies, and that those galaxies were on the orders of hundreds of thousands of light years across, and in fact separated by millions of light years from each other and stuff like that. So they had this small idea of the universe, but in order to make it make sense with the observations they had made, because they were constantly trying to predict where the planets would be at certain times of the year, 10, 20, 15 years in advance, because they had to make decisions based on what they thought was a real science called astrology, but it's actually a pseudoscience, and you can't really make any predictive values out of it because you can literally have two astrologers that reach exactly the opposite conclusion in any scenario. But still, that's how people like Copernicus and Galileo and Tycho Brahe, that's how they actually made a living, was by calculating the positions of the planets far into the future and making what was called almanacs, and those almanacs would be sold so that you could or published so that the leaders could design holidays and actually do things like make decisions based on when they were born, whether or not to get married, whether or not to go to war, that kind of stuff. So they did all that, but the system that they were using was the Ptolemaic model, and that had basically the Earth at the center. They had actually considered the Earth not being at the center. The ancient Greeks even considered that, and in fact, they had to throw it away because the ancient Greeks knew that if in fact we were orbiting around the sun, if the Earth was orbiting around the sun, then when the sun is here and the Earth is over here, and we look at a distant star, when we move over to here, that same distant star would be in a different spot in outer space relative to farther away stars. That's called parallax. And they said if this is really happening, if the Earth is really orbiting around like the sun, then we should see stars that are closest to us move back and forth from here, and when we're in here, they'll move back and forth like this. But they couldn't detect any of that, so they had to make one of two conclusions. Either the universe is really, really huge, so huge that they couldn't detect that parallax, or that they were the center. They just couldn't imagine the universe was that big, so they threw that idea out and they stuck with the sun or the Earth-centered or the geocentric universe. Well, to make that work, which is completely wrong, right? You have the Earth with the moon orbiting it, and then outside of that, you have the sun orbiting that, and then outside of that, you have Mercury orbiting the Earth, and then outside of that, you have Venus orbiting that as well, and then Mars, and then Jupiter, and then Saturn. Well, as luck would have it, none of that worked out too well, and they were, sort of hemmed in by the ideas of Aristotle, which basically said that in the heavens everything was perfect, and the perfect shape is the sphere or maybe the circle. So that meant that everything that was moving in outer space, one, could not slow down or speed up, and two, had to follow either spherical paths or circular paths. And in order to make that happen, even though we saw, for instance, if you look up in the constellation of Gemini, for instance, in June or somewhere, or maybe in January or something, you would occasionally see a wanderer, which the Greek word for wanderer is planetos, and you would see this wanderer who would be right here one day, and then 2 weeks later it'd be here, and then 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 here. They would literally come through and do a loop to loop. How in the heck can you make that a circle? Well, what they ended up doing is circles inside of circles. So basically, their model was something like this. So you would say, uh, here's Earth right here, and then here was the moon, and the moon would orbit like that. And then here was the sun, which is ginormous. Of course, they didn't necessarily understand that, but here's the sun. And then they would have, for instance, Mercury like that. But to make sense of Mercury never getting very far from the sun, they imagined that there was an imaginary line that went from the center of the earth through the sun, and then on that was a circle on a circle called an epicycle, and that Mercury itself was on that epicycle moving around in a circle, and the center of that epicycle always stayed along that line. However, they also had a problem in that Venus also didn't deviate far from the sun, so it also had to have a epicycle that was centered on that line, and therefore we had Venus like that. And you still also had the other planets that had similar things going on, only they didn't have to stay so close to the Earth, so they would have an epicycle like this, and that would be Mars. And then there would be another epicycle, for instance, farther away still, and that epicycle would be for Saturn, and then another epicycle again, and that epicycle would be for Jupiter. That was their model, and that still wasn't good enough. They actually had to make what's called an equant point, the point at which wasn't the center of the Earth, but it was from it where if you sat at that equant point, then it looked like the planets were actually moving at a constant speed. So it had all this crazy stuff. They had spheres inside of spheres inside of spheres and all this crazy stuff, and it was just really ugly. But every year it had so many variables. Every year, 10 years, 20 years, they could take all the observations that they had since the last almanac they made, and they could curve fit it until they got everything to match the past. And then that would predict the future for the next 10, 20 years or whatever. And that was the Ptolemaic model. Well, Copernicus didn't complain about it not matching data. He didn't complain about experimental results. What he complained about was us deviating from what the ancients taught us. Specifically, he said we lost our way from what Aristotle said. So Copernicus comes along and says it's much better if we just take the sun at the center, and then it makes perfect sense why the orbit of Mercury is the shortest period one, and then Venus is the second shortest period because it's just outside of it, and then outside of that is Earth. Whoa, don't know what happened there. Okay, there you go. Outside of that was the orbit of the Earth, and then outside of that was the orbit of Mars, and then outside of that was Saturn, and then outside of that was Jupiter. But he had that all of these things had to be moving in circles and that the planets couldn't speed up or slow down. They had to go at a fixed speed, all because that was what Aristotle taught. So I do not call the Copernican revolution the same thing as the scientific revolution because Copernicus was not increasing science. He was sticking back to the ancients or trusting the ancients in some sense. In fact, what I call the Copernican revolution is the idea that for instance, if you've seen these T-shirts where it has a big spiral galaxy on it, and then it has this little arrow pointing this insignificant dot, and it says "You are here," that's a continuance of the Copernican revolution. It's the idea that the Earth isn't the center of the universe; it's just the third planet, which is not very big, around a star that's not that impressive in a galaxy that's not that big, and that's a continuous of the Copernican revolution. Just like evolution and the tree of life, the idea that all species are have an origin with a single common species way, way, way back in the distance makes all of us not the super most important thing, but all of us parts of a bigger system. So that's the Copernican revolution. The scientific revolution was brought along by Galileo, who said, no, this crap can't work because I can look and see that, for instance, Jupiter has four moons that orbit it, and that's completely contrary to the motion that we've seen. So I've got to understand motion. So this was the idea they had. Kepler comes along and he has a very specific idea. He thinks that it's not a coincidence that the number of planets is exactly the right number of planets for the number of perfect solids that exist to be exactly the spacers between the spheres that contain the planets. So he imagined a Copernican revolution or a Copernican universe where the sun was at the center, but then the sphere for Mercury was separated from the sun's sphere by one of the perfect solids, and then the sphere for Venus was separated from the sphere of Mercury's orbit by another perfect solid, and so on and so forth. And he tried to work that out once he got to employed by Tycho Brahe, but it just didn't work out. So ultimately, he had to throw all that away, and he came up with these three laws: Kepler's first law, Kepler's second law, Kepler's third law. So Kepler's first law is the planets orbit the sun in elliptical orbits with the sun at one focal point. Now that's a big deal because Aristotle said everything had to be circles, and an ellipse is not as bad as an oval, which is a truly bastardized circle, but an ellipse is also a bastardized circle to some extent. But at least it has a nice mathematical structure as part of the conic sections. So how would you go about making a circle versus a ellipse? Well, if you stuck a nail in a piece of plywood and then you tied a rope to that nail and then you tied the other end of that rope to a pencil and you worked real hard at holding that rope tight and keeping that pencil vertical, and you went around like that, that would make a circle. If you did it really well and practiced hard, you could probably get a nice circle out of it. If you want to make an ellipse, you put two nails in the plywood and you then tie a rope to both nails, but the rope has to be longer than the distance between the nails. And when you do that, you get something like this. So here's a nail and here's a nail, and you of course connect it with a rope of fixed length, and there's your pencil like that. Well, if you allow that to stay taut and trace it out, it'll come out like this, and that's an ellipse. This distance is called the major axis, and this distance is called the minor axis. And of course, if you go from the center to the end, that distance is called the semi-major axis. and it's really one half of the major axis. But notice the nails are the focal points. So what we could imagine is the sun would be one of these. So now if you look at it, you'd say, oh, wait a second. The distance from here to here, which is what we call the perihelion distance, that's the distance of closest approach to Helios, the sun. That little distance is the distance at which the planet is closest to the sun. But then if you look right here, this distance from here to here is the distance at which the planet is farthest from the sun. If you take that distance that's closest to the sun and add to it that distance that's farthest from the sun, then you get the major axis. And then if you divide that by two, you get the average of those two distances. And in that sense, the semi-major axis is the average distance between the sun and the planet. Okay, that's going to become relevant in a second. So let's call this A, let's call this B, and then S equals the semi-major axis, which is a concept, a geometric thing, and a number. It's going to be A plus B over 2. That's our semi-major axis. So it's also called, like I said, the average distance or the average orbital distance for the planet. So what Kepler's first law says, the planets orbit the sun in elliptical orbits with the sun at one focal point. And we can determine things about this. For instance, the closer the ellipse is to a circle, the closer the eccentricity, the lowercase e that you see in your book, is to zero. And the more elliptical it gets, the more stretched it gets. In other words, the closer the ellipticity or the eccentricity comes to one. So that's a key parameter as well. Then the second law, Kepler's second law, says oops, the planets sweep out equal areas in equal time. So if you imagine an ellipse like this and the sun right here, if this is an area A1 and maybe this is day 1 and this is day 20, then if you take this little piece of pizza, if you will, and you say that area is A1 as well, notice it's a lot longer so it can be narrower, then this too is day 1 and this too is day 20. So what that shows you is the planets go slower when they're far from the sun and speed up when they're near the sun. Again, another rejection of Aristotle's ideas. So that's what the equal areas and equal times come. Newton comes along with his law of gravity and is able to show that this is just a conservation of angular momentum thing. Uh, Even though I'm not sure he actually had that. I have to look back at my Principia to make sure. Finally, the Kepler's third law is the square of the period of an orbit is proportional to the cube of the semi-major axis. So that means t squared is proportional to s cubed. And in fact, if you take g m over r squared is equal to mv squared over r, and you of course cancel out one of those r's, but you also say v is equal to 2 pi r over t, then you can get, obviously the m's are going to cancel out again like we did, but you're going to get now g times big M over r is equal to 4 pi squared r squared over t squared. Remember the v was squared, so that's why the 4, the pi squared, and the r squared, and the t squared are there. And from this, you can see that t squared is equal to 4 pi squared over gm times r cubed. That is the expression of Kepler's third law, and that even gives you what that constant is. The constant of proportionality would be 4 pi squared over gm. So that is Kepler's three laws of planetary motion. They're what we call epistemological, in that he was able to show with the data that these were the facts about the orbits, but he had no fundamental idea of why that was so. When Newton comes on later on and comes up with the law of gravity, one of the first things he does is he's able to show that the planets orbit in elliptical orbits, which is consistent with Kepler's third law. But he goes even farther, or first law, excuse me. But he goes even farther and says that they can do ellipses, they can do circles, they can do parabolas, and they can do hyperbolas. He's able to show that the planets sweep out equal areas in equal times, basically using the calculus, and he's able to show that the square of the period is proportional to the cube of the semi-major axis. We can see that Kepler's second law is a result of conservation of angular momentum, and we can see that the Kepler's third law is a result of conservation of energy. But he didn't have any of that. Neither did Newton necessarily know that. But Newton had discovered his law of gravity and was able to show that these were ramifications of it. So that's a pretty big deal. In order for you to actually use it, for instance, it's very common for me to give you, for instance, this equation that I just boxed off. I can give you that in t in years squared is equal to S, the semi-major axis. Remember, I used R here, but as I drew in that diagram a second ago, S is a semi-major axis. If we put that in astronomical units, then it would just be T squared in years is equal to S cubed in astronomical units. And the reason why we know that's true is because the Earth has a period of 1 year, so T squared would be 1 year, and Earth has a semi-major axis of 1 astronomical unit, and 1 cubed is 3. So 1 squared equals 1 cubed, and therefore that must be the value. So that's actually another way you can use Kepler's third law to calculate the size of orbits if you know the period, or if you know the size of the orbit, you can use it to calculate the period. Uh, you can see some simple examples in your book. For instance, example 6.7 does that. It says Mars period was noted by Kepler to be about 687 days, which is 1.88 years. Determine the mean distance of Mars from the sun. So if you wanted to do that, you could just say, I do have a, oh, nope, time's up. Anyways, I'm going to finish that. You guys are free to go. Time's up, but I'm going to go ahead and do that example 6.7 and just have it here on the end. You're free to go. I did post your lab. Actually, not your lab. You have a different lab, so never mind that. But have a good weekend, everybody. Keep an eye out for your emails for those the chance to make up that missed face-to-face test. Also, if you have an online test that you missed, you are going to lose points for probably for the face-to-face test being missed, and you're also going to lose points for missing the online test. But if you let me know that you missed them and you're not wanting to be dropped from the class, then I'll do my best to go ahead and give you some extension on that. But you got to email me or text message me, one of the two. Don't forget, whenever you email me or text message me, you give me your first and last name, and you got to tell me what class you're in. Have a good one, everybody. I'm going to work example 6.7 and wait here for the last person to leave in case you have any questions.
Hey, sorry, I just had a question really quick.
Yeah, no problem.
Um, the practice test is due today, but the online and face-to-face tests aren't until next week. So I was wondering if that's a mistake or if you could possibly move it like later.
No, it's the online test is due today because that's on two separate chapters, and then another set of chapters comes up before we get to the face-to-face test. So there's actually going to be two online tests before that. That's why I made this one this date. You say it's due today?
Yeah, I don't see an online test due today as well.
Uh, Let me check that real quick. Then that's a problem. Let's see. Here we are. Okay, so I'm looking at the practice test. Practice test two, chapters 3 and 4 is due June 18th, which is today. And then if I look at online tests, oh, okay, it's been changed to June. It was supposed to be changed a long time ago when I changed your syllabus, so that was actually supposed to be the 18th. What I'm going to do is I will make this, let's see, 19, 20, 21. I'm going to make that the 22nd, and then I'll make the practice test due on the 22nd as well.
All right, thank you so much.
No problem. Sorry about that. I can't believe that messed that up, but that's pretty bad. Anybody else?
All good.
Thanks,
Have a
bud.
good rest of your night.
You too. Looking at example 6, 7, which says, where is Mars? Mars's period, its year, was noted by Kepler to be about 687 days, which is 1.88 years. Determine the mean distance of Mars from the sun using Earth as a reference. So what they want to know is S for Mars. That's what we're using for the semi-major axis. I often use A. That's almost always what I use, but that's what they're looking for. So what we know from the derivation I just did was, and I usually like it to write it as r cubed by itself. So I'd say solution r cubed is equal to gm over 4 pi squared. Make sure I'm copying that right. Gm over 4 pi squared times t squared. So if I say t earth squared, actually I should probably use the symbol that we have for earth already, which is a circle with a plus symbol. So t squared is equal to gm over 4 pi squared times s cubed, and then T Mercury squared is equal to GM over 4 pi squared S Mercury cubed. We could imagine dividing those two equations. We could say 1 divided by 2. Now, this is a nasty way of, or a nastier way of doing it. I'll show you another way in a second, but this is sort of what I think the author is asking for us is determine the mean distance of Mars from the sun using the Earth as a reference. So I'm trying to use these two equations like this. So this is going to become T squared over T Mercury squared is equal to gm over 4 pi squared over gm over 4 pi squared times s cubed for the Earth over s cubed for Mercury. And obviously you can see that all that cancels out with all that. And what we're able to do is say that the s for Mercury cubed is equal to the t for the Earth squared over the t for Mercury squared. Actually, I think I have to do that upside down. Yes, I do have to do that upside down. So just fixing that, I'm going to reverse it by putting this up here and that up down there. So that's going to be Mercury here, and that's going to be Earth down here. And then, of course, when I'm solving it for S Mercury, that means that that's going to be on top, and then Mercury's going to be on top, and the Earth will be on the bottom, and then it's times the semi-major axis of Earth cubed. And we know that the period of Mercury is 1.88 years, and the period of the Earth is 1.00 years. And that quantity is going to be squared. And then we also know that the semi-major axis of Earth is 1 astronomical unit, and that's going to be cubed. So the semi-major axis of Mercury cubed will equal 1.88 squared, and that gives me 3.534. times 1 astronomical unit cubed, like that. And that gives me 3.534 astronomical units cubed. So now that's S Mercury cubed. So I take the cube root of both sides, and that means taking the cube root of 3.534. So I'm going to raise it to the 0.33333 power, and that gives me S Mercury is equal to 1.523 astronomical units. And actually, I think this is supposed to be Mars. I don't know why I was writing Mercury. Yeah, I wrote Mars as part of it. It is Mars, by the way. And that's what made me know did it wrong, because 1.52 is the data for Mars, not for Mercury. So I apologize for writing Mercury here and then all these other stupid places. Actually, it probably would have been really easy just to change that to MAR instead of MER, but here we are. So I'm going to say MAR, 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 and of course this last one was also MAR. So that's actually the way you can do it, but I want to show you that that's really nasty. It's nice because it's a way of bypassing using the 4, the G, the pi squared, and the M, but by using the other equation that I showed you, S cubed in astronomical units is equal to T squared in years, then we can use that alone to figure out what the semi-major axis of Mars is. Specifically, S Mars cubed is equal to 1.88 years squared, which gives me 3.5334 years squared. Oop, let's double check that. 1.88 squared is 3.534. That's right. Now I'm going to take the cube root of both sides. The cube root of S Mars cubed is equal to the cube root of 3.534 years squared, which obviously doesn't give us the right units, but I'm going to be ditching those units anyways. So the cube root of 3.55 or 3.534 is in fact 1.523. And of course, that has to come out in astronomical units. So that's another way. So you don't actually have to do all that stuff I did. You just have to realize that there's a 1 in here, and that 1 has units of astronomical units cubed over years squared. So that's what the actual constant is between the equals and the t. So you can use that instead of the method that I used above with all the blue, but hopefully that helps you. Uh, we have now completed chapter 6. There's a example 6-8 that might come in kind of handy. There's also, let's see if there's any other examples that jump out at me. Lagrange point, that's an interesting one. I would certainly like y'all to learn how to do that. I probably wouldn't ask that on the test, but it's certainly fair game uh, for a homework, and maybe even pop up on a practice test. I just wouldn't give you that in test. Then we talk about forces of nature. And then we talk about gravitational field. Those sections are really optional. So we're essentially finished. I'll talk a little bit next time about general relativity and explain a little bit more about that, but we're essentially done with chapter 6. This is plenty of examples. If anybody has any questions, make sure you ask me. But that's it. Thank you for coming, everybody. Have a good day, and I'll see you next week. Bye bye.